Let us begin very gently with a story that feels impossible the first time we hear it. Imagine a hotel with infinitely many rooms. Not merely many rooms. Not 1,000,000 rooms, not 1,000,000,000,000 rooms, not more rooms than anyone could ever build. Imagine a hotel whose rooms continue without end. Room 1, room 2, room 3, and so on forever. There is always another room number beyond the last one you have mentioned, because there is no last one. Now imagine that every room is occupied. Every guest is already settled. Every room number has someone inside. The hotel is completely full. In the ordinary world, that would settle the matter. A full hotel has no vacancy. If a new traveler arrives at the desk and asks for a room, the answer must be no. Full means full. But here is where our finite intuition begins to loosen. In this infinite hotel, one new guest arrives and the hotel manager says, very calmly, yes, of course, we can make room. How? The manager asks the guest in room 1 to move to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. Each guest shifts one room forward. Every current guest moves from a room to the next room. Because there are infinitely many rooms, this process never runs out of space. No one is pushed out of the hotel. Every guest still has a room. And now room 1 is empty for the new arrival. So the hotel was full, and yet one more guest was accommodated. This is the first strange break from finite thinking. In a finite hotel, if every room is occupied, there is no room left. That is obvious. But in an infinite hotel, being full does not mean there is no capacity for more. Fullness and impossibility of extension come apart. That is deeply unfamiliar at first, and it is worth sitting with that discomfort. Let us pause and reflect on what has happened. Nothing mysterious occurred in the sense of logic. No contradiction was allowed. No guest was doubled. No room held 2 people. No guest disappeared. What changed was our background assumption about what it means for a collection to be complete. In the finite world, a complete occupied collection cannot be enlarged without overflow. In the infinite world, that inference fails. And this is why Hilbert's hotel matters so much. It is not a joke and not merely a clever story. It is a doorway into a precise mathematical way of thinking. It teaches us, almost by force, that infinity does not obey the habits of ordinary counting. Now let us continue a little more slowly. Suppose not one new guest arrives, but 10 new guests. Again, in a finite full hotel, this is hopeless. But in the infinite hotel, the manager simply tells each present guest to move 10 rooms forward. The guest in room 1 goes to room 11. The guest in room 2 goes to room 12. The guest in room 3 goes to room 13, and so on. Then rooms 1 through 10 are empty, ready for the new arrivals. So not only can a full infinite hotel admit one more guest, it can admit finitely many more guests all at once. And then the story becomes even more striking. Suppose infinitely many new guests arrive. Not 10. Not 100. Not even 1,000,000. Imagine a new bus carrying infinitely many guests, each one needing a room. The original hotel is still full. Every room still has an occupant. And yet the manager still says yes, there is room for everyone. This time the manager uses a different strategy. Each current guest is moved from their room to a room with an even number. The guest in room 1 goes to room 2. The guest in room 2 goes to room 4. The guest in room 3 goes to room 6. Each old guest goes to double their room number. Now every even-numbered room is occupied by one of the original guests, and every odd-numbered room is empty. But there are infinitely many odd-numbered rooms. So the infinitely many new guests can be placed into room 1, room 3, room 5, room 7, and so on. A full hotel has absorbed infinitely many additional guests. Again, it is worth repeating, this is not a trick. It feels like one only because our minds are trained on finite collections. The paradox is not in the mathematics. The paradox is in the conflict between mathematical truth and everyday expectation. This is the central lesson of the hotel story. Once a collection is infinite, fullness is not the same as exhaustion. An infinite collection may be put into correspondence with a part of itself, or extended while still somehow retaining the same overall size in the relevant mathematical sense. And that phrase, the relevant mathematical sense, now leads us to the next idea. What does it mean for 2 sets to have the same size? In the finite world, we are used to answering this by counting. One set has 5 objects, another set has 5 objects, so they are the same size. One set has 7 and another has 4, so they are not the same size. But if the sets are infinite, ordinary counting never comes to an end. So we need a more flexible and more fundamental notion. That notion is pairing. 2 sets are said to have the same cardinality, or the same size in the mathematical sense, if we can match their elements perfectly. Every element of the first set is paired with exactly one element of the second set, every element of the second set is paired with exactly one element of the first, and nothing is left unmatched. This is called a bijection. Let us say that again in slower language. A bijection is a perfect one-to-one correspondence. No element on the first side is used twice. No element on the second side is used twice. No element is omitted. No leftovers remain anywhere. If such a perfect pairing exists, then the 2 sets count as having the same size. For finite sets, this agrees with ordinary counting. If 2 finite sets can be perfectly paired, then they have the same number of elements. So this new definition does not overthrow finite arithmetic. It extends it. But for infinite sets, it reveals new behavior. Hilbert's hotel is really a story about bijections. When each guest in room number n moves to room number n+1, or to room number 2 times n, we are describing a correspondence between one infinite set of room numbers and another. The hotel remains manageable because the rooms can be rearranged in a systematic way, preserving a one-to-one assignment. The story becomes clearer when we translate it into the language of sets. Consider the natural numbers. These are the counting numbers beginning with 1 and continuing forever, or depending on convention sometimes beginning with 0. For our purposes, the exact starting point will not matter very much. What matters is that they can be listed in an endless sequence. Now consider the even natural numbers. 2, 4, 6, 8, and so on. At first glance, the even numbers seem to be only half of the natural numbers. They are a proper subset. They leave out all the odd numbers. So finite intuition says the even should be smaller. And in one sense they are a part of the whole. That is true. But in the sense of cardinality, they are the same size. Why? Because each natural number can be paired with exactly one even number by doubling it. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6, 4 pairs with 8, and this continues forever. Every natural number gets one even number. Every even number comes from exactly one natural number. Nothing is missed and nothing is repeated. So the natural numbers and the even numbers have the same cardinality. This is one of the signature facts of infinity. A proper subset of an infinite set can have the same size as the whole set. That never happens for finite sets. If you remove elements from a finite set, it gets smaller. That is unavoidable. A set of 5 objects cannot be paired perfectly with a proper subset of itself. There will always be leftovers on the larger side. But infinite sets are different. Their structure allows this self-similarity in size. A part can be as large as the whole in the precise sense of one-to-one correspondence. It is worth repeating because it is one of the great dividing lines between finite and infinite mathematics. For finite sets, proper subset means smaller. For infinite sets, proper subset need not mean smaller. Once we understand this, Hilbert's hotel becomes less magical and more logical. The reason the full hotel can accommodate more guests is that the set of all occupied rooms can be matched with the proper subset of the room numbers, leaving other rooms free. So the hotel story and the definition of cardinality are not separate topics. They are 2 views of the same phenomenon. Now let us focus on one important type of infinity. A set is called countably infinite if its elements can be listed in a sequence. That is the key idea. There must be some ordering in which we can say first element, second element, third element, and so on forever, with every element eventually appearing somewhere on the list. This does not mean the set is physically small, or sparse, or simple. It means only that its elements are enumerable in sequence. That is why the word countable can be slightly misleading at first. In everyday speech, countable may sound like manageable or not too large. But in mathematics, a countable set may still be infinite. What countable really means is listable. If a set can be placed in a one-to-one correspondence with the natural numbers, then it is countably infinite. The natural numbers themselves are the basic model of countable infinity. Their cardinality is sometimes denoted by a special symbol, read as aleph null. You can think of this as the name for the size of the natural numbers, and therefore also the size of any set that can be perfectly matched with them. So when we say a set is countably infinite, we are saying it has the same cardinality as the natural numbers. Let us rest there for a moment. Countable infinity is the first infinite size. It is not the only infinite size, as we will later discover, but it is the first one we meet. It includes many sets that seem, at first glance, very different from one another. The natural numbers are countable. The even numbers are countable. The odd numbers are countable. And soon we will see that the integers and the rational numbers are countable too. That may feel surprising, especially for the rational numbers, but the guiding principle remains the same. The question is never whether the set feels crowded on the number line, or whether it seems denser, or whether it contains more kinds of numbers. The question is whether its elements can be arranged into a sequence so that each element appears exactly once. Countability is about enumerability, not visual abundance. Now let us turn to the integers. The integers include 0, the positive whole numbers, and the negative whole numbers. So in addition to 1, 2, 3, and so on, we now also have -1, -2, -3, and so on, extending forever in the negative direction. At first, it may seem that adding all the negative numbers should create a strictly larger infinity. After all, the natural numbers go off in one direction, while the integers go off in two. Surely that must make a difference. But again, the test is not geometric appearance. The test is whether the integers can be listed in sequence. And they can. One simple list is the following, in words: 0, then 1, then -1, then 2, then -2, then 3, then -3, and so on. This sequence alternates back and forth, each time reaching one step further from 0. If we continue forever, every integer eventually appears. 0 appears immediately. Each positive integer appears at some stage. Each negative integer appears at some stage. So the integers can be listed. Therefore the integers are countable. That means the set of all integers has the same cardinality as the set of natural numbers. This is another good moment to reflect. We have now enlarged our world from natural numbers to all integers, adding infinitely many negative values, and yet the cardinality has not changed. The size in the sense of bijections remains the same. Once more, clever ordering is the key. Infinity often resists first impressions, but yields to systematic arrangement. And this is worth repeating because it is one of the most useful habits in this subject. When faced with an infinite set, do not trust your first visual sense of how big it is. Ask instead whether it can be organized into a sequence. Now we come to the rational numbers. These are the numbers expressible as fractions of integers, with non-zero denominator. In ordinary language, they include numbers like 1/2, 3/4, -7/5, and also whole numbers, since any whole number can be written as a fraction. The rational numbers are everywhere dense on the number line. Between any two distinct real numbers, no matter how close, there are infinitely many rationals. Between 0 and 1 alone there are already infinitely many rational numbers. So the rationals seem much more numerous than the integers. The integers are spaced apart. The rationals are packed everywhere. And yet, astonishingly, the rationals are also countable. This is one of the great lessons in the difference between density and cardinality. A set may be densely spread through an interval and still have the same cardinality as a set that appears much more discrete. Density concerns how a set sits inside space, especially inside the number line. Cardinality concerns whether the elements can be matched one-to-one with another set. These are different questions. Let us linger on this because it is easy to blur them together. The integers are not dense. There are gaps between them. The rational numbers are dense. Between any two rationals there are more rationals, endlessly many. But density does not by itself imply a larger cardinality. The rational numbers can still be listed. How can that be done? The classical idea is to imagine the positive rational numbers arranged in a grid. The numerator runs across one direction, the denominator across the other. So 1/1 appears somewhere, then 1/2, 1/3, 2/1, 2/2, 2/3, and so on. This grid is infinite in two directions. At first it looks impossible to turn it into a single list. But one can trace through the grid diagonally, moving through entries in a systematic path. In doing so, every fraction will eventually be encountered. There is a small complication. some fractions appear more than once in different forms. For example, 1/2 and 2/4 represent the same rational number. So when building the list, we simply skip repeated representations and keep only the first appearance of each rational number. The important point is that a sequence can be constructed that eventually reaches every rational number exactly once. Therefore, the rational numbers are countable. Let us say that again, because it is one of the most beautiful surprises in elementary set theory. The rational numbers, despite being infinitely dense on the number line, can still be placed in a sequence. So their cardinality is the same as that of the natural numbers. This tells us something profound. Spatial richness is not the same as set theoretic size. A set can feel omnipresent, filling every interval with infinitely many points, and still belong to the smallest infinite cardinality. It is worth pausing here and summarizing what we have learned so far. We began with Hilbert's hotel and discovered that a full infinite collection can still make room for more. We then translated that story into the formal language of bijections, or perfect pairings. We saw that infinite sets differ from finite ones in a crucial way. A proper subset of an infinite set may have the same cardinality as the whole. We introduced countable infinity as the size of the natural numbers, meaning the size of any set whose elements can be listed in sequence. And then we saw that the integers and the rational numbers, although they appear far more extensive than the natural numbers, are nevertheless countable. So one might now ask a perfectly natural question. Are all infinities the same size? It is an understandable thought. We have already encountered several different infinite sets, and each time the answer has been the same. Natural numbers, even numbers, integers, rationals. Different shapes, same cardinality. Different appearances, same size. So perhaps infinity is just one thing. Perhaps all infinite sets are equivalent once we measure them by bijection. That would be a reasonable guess at this stage. But it is not correct. And here the subject deepens. There are larger infinities. The set of real numbers, the full continuum of points on the number line, is not countable. It cannot be listed in a sequence. No matter how cleverly we try to arrange them, no matter what order we choose, there will always be real numbers missing from the list. This is the great turning point in the study of infinity. Until now, infinity has challenged finite intuition by showing surprising equivalence. Now it challenges us more deeply by showing genuine inequality among infinite sizes. Infinity is not one undifferentiated vastness. It has internal structure. It comes in levels. To appreciate this, let us think carefully about what the real numbers are. The real numbers include the rational numbers, but also many others that are not fractions. They include numbers whose decimal expansions do not terminate and do not eventually repeat. They include familiar rational numbers, but far more besides. In fact, most real numbers are not rational. Every point on the continuous number line corresponds to a real number. And Cantor showed that the real numbers cannot be counted. Not counted in the sense of finishing a tally, of course, because no infinite set can be counted to completion that way. Rather, not counted in the technical sense of being listable in sequence. No list of real numbers can ever contain them all. The standard proof of this is Cantor's diagonal argument. Let us explain its spirit slowly and intuitively. Suppose, for the sake of argument, that someone claims to have listed all the real numbers between 0 and 1. They produce a sequence: first real number, second real number, third real number, and so on forever. Now write each of these numbers in decimal form. So there's a first row of digits for the first number, a second row of digits for the second number, a third row for the third, and so on. Cantor's idea is to build a new real number by inspecting the diagonal digits of this infinite list. From the first number, take the first digit after the decimal point. From the second number, take the second digit. From the third number, take the third digit, and so on. Then alter each of those chosen digits in some simple way, making sure the new digit differs from the original one. The resulting number has a remarkable property. It differs from the first listed number in the first decimal place. It differs from the second listed number in the second decimal place. It differs from the third listed number in the third decimal place. And so on forever. Therefore, it cannot be equal to any number on the list, because for each listed number there is at least one digit position at which they differ. So even though we started with an alleged complete list of real numbers, we have explicitly constructed a real number missing from it. That is the contradiction. Therefore no complete list can exist. Therefore the real numbers are uncountable. This proof is extraordinarily powerful because it does not merely show that one particular list fails. It shows that every possible attempted list must fail. No matter how ingenious the listing method, the diagonal procedure escapes it. It is worth repeating the emotional significance of this. The real numbers are not just another infinite set alongside the naturals, integers, and rationals. They form a strictly larger infinity. There are more real numbers than natural numbers, in the sense that no bijection exists between them. This is one of the most profound discoveries in mathematics. Let us pause and reflect again. We began with a hotel paradox showing that infinite sets can behave in ways finite sets never do. We learned to replace naive size with bijective correspondence. We found many apparently larger sets that still turned out to be countable. And now, at last, we have reached a boundary. The real numbers cannot be compressed into a sequence. The method of listing, which worked for naturals, integers, and rationals, fails completely here. So not all infinities are equal. Some are genuinely larger. And this gives mathematics a new kind of landscape. Infinity is no longer a single misty horizon. It becomes a hierarchy. This is the spirit of Cantor's discovery. There are different sizes of infinity. That single sentence changed the foundations of mathematics. In a sense, Hilbert's hotel teaches elasticity within one infinite size. It shows how a countably infinite set can absorb additions without changing cardinality. Cantor's theorem, in spirit, teaches transcendence beyond that size. It shows that from one level of infinity, mathematics can move to a still greater one. One way to glimpse this broader principle is through the idea of a power set. Given any set, one may form the set of all subsets of that set. Cantor proved that the collection of all subsets is always strictly larger in cardinality than the original set, even if the original set is infinite, even if it is already enormous. Its power set is larger still. This means there is no largest infinity. Whenever one infinite cardinality is given, a larger one can be formed. The subject opens upward without end. And here again it is worth slowing down, because this can be conceptually disorienting. Many people, before encountering this theory, imagine infinity as a final ceiling, something beyond all numbers, beyond all magnitudes, beyond all comparison, a single ultimate vastness. Cantor showed that this image is too simple. Infinity is not one thing. It is a structured domain with distinctions, comparisons, and ascending levels. The infinite is not mathematically featureless. It is richly articulated. This is one of the reasons the subject feels both unsettling and beautiful. It takes what seemed vague and makes it precise. It takes what seemed ungraspable and gives it form. Let us now gently revisit the main themes, because repetition is especially helpful in this topic. Hilbert's hotel tells us that infinite collections behave differently from finite collections. In the finite world, full means no vacancy. In the infinite world, full may still permit rearrangement and expansion. The correct tool for measuring size is not subtraction from a container, but one-to-one correspondence. A bijection is a perfect pairing with no leftovers and no repetition. This becomes the right notion of equal size once counting cannot terminate in the ordinary way. A set is countably infinite when it can be listed in sequence, meaning matched with the natural numbers. Countable does not mean sparse, and it does not mean physically small. It means innumerable. The even numbers are countable. The integers are countable. The rational numbers are countable. This last fact shows, very clearly, that density is not the same as cardinality. And then the real numbers break the pattern. They cannot be listed. Cantor's diagonal argument shows that any supposed complete list misses at least one real number. Therefore the real numbers are uncountable. So there are at least two distinct infinite cardinalities already before us, the countable infinity of the natural numbers and the larger uncountable infinity of the real numbers. And beyond that there are more. It is worth repeating, perhaps one final time, the deepest contrast between finite and infinite size. For finite sets, the part is always smaller than the whole. For infinite sets, the part may equal the whole in cardinality. But not every infinite set has the same cardinality. So infinity is neither finite-like nor utterly uniform. It is its own world with its own rules. That is why this topic is so memorable. It does not merely extend ordinary arithmetic. It asks us to revise our intuition about size itself. And yet, once the new definitions are accepted, the subject becomes calm again. The paradoxes soften. What at first seemed impossible becomes a natural consequence of precise language. This is often the way in mathematics. Confusion is not always a sign of error. Sometimes it is the sign that an old intuition is being replaced by a better one. Hilbert's hotel feels impossible only until we understand that infinite occupancy does not prohibit rearrangement. The even numbers feel smaller only until we understand bijections. The rational numbers feel too abundant to count only until we discover that sequence is different from density. And the real numbers feel perhaps similar to the rationals only until diagonalization reveals their greater cardinality. Each step is a refinement of thought. Each step replaces appearance with structure. And each step opens the subject a little further. Let us move now into a slow concluding summary. We imagined a hotel with infinitely many rooms, all occupied, and yet still able to welcome one more guest, then finitely many more guests, and even countably infinitely many more guests. This taught us that infinite fullness is unlike finite fullness. We then introduced the idea of cardinality through bijection, a perfect pairing with no omissions and no repetitions. This is the mathematical meaning of equal size for arbitrary sets. We saw that the natural numbers and the even numbers have the same cardinality, even though one is a proper subset of the other. This revealed one of the central features of infinite sets. We defined countable infinity as the size of any set that can be listed in sequence, and we noted that this size is represented by the cardinality of the natural numbers. We found that the integers are countable because they can be arranged in a sequence that alternates outward from 0. We found that the rational numbers are also countable, despite being dense on the number line, because they too can be systematically listed. Then we asked whether all infinities are the same, and the answer was no. The real numbers are uncountable. Cantor's diagonal argument shows that every attempted list fails. Therefore the reals form a strictly larger infinity than the naturals. And beyond this lies a broader vision. Mathematics contains not one infinity, but an ascending hierarchy of infinities. So the study of infinity does not end by reaching a single boundless object. It begins there. It opens into structure, comparison, and depth. If you have drifted in and out while listening, that is perfectly all right. The essential ideas are gentle enough to return to. A full infinite hotel may still make room. Equal size means perfect pairing. Countable means listable. Integers and rationals are countable. Reals are not. There are different sizes of infinity. And perhaps that final thought is the one to rest with. Infinity is not a blur. It has shape. It is not a single and distinct beyond. It has levels. It is not the collapse of mathematics, but one of its great clarifications. And once we accept that, the strange hotel at the beginning no longer feels like a paradox meant to mislead us. It feels like an invitation to step beyond finite habits of mind and to see that even the infinite can be studied with patience, precision, and quiet understanding.